Hey physics students, going to do this friction 1 sheet. What we have added now to what we know about unbalanced forces and finding accelerations and all that is that the force of friction is equal to this coefficient of friction, mu, times the normal force. So I'm just going to write that equation right here. Definitely going to use that. Okay, so let's see what we got here. A sled weighing 300 newtons, that is the gravitational force. Gravitational force and weight are the same thing. Notice that that's measured in newtons, right? So we don't have to multiply that by 10. It's already done. It's moving at a constant speed. That means forces are balanced over a horizontal floor. So no angles, by a force of 50 newtons applied to the floor. Okay, so I'm going to work on this force diagram here. The force of gravity is 300 newtons. And the force that's pulling it, what does it say? Pull moves across. It says moved. Push or pull, I don't know. I'll just do, how about FP? Could be a push or a pull. Don't know. Okay, now if it's moving at a constant speed, then the forces must be balanced. So that means, of course, the support force, or normal force, as usual, will balance the gravitational force. And if it's going at a constant speed, that means the friction force must be balancing that. All right, force diagram complete. Part B, determine the coefficient of kinetic friction, mu, between the sled and the floor. We're only going to deal with this whole coefficient of friction. I meant to delete that so we didn't get confused about that, but it just means the mu. So I'm just going to find this. And hey, look, I know what the friction force is and what the normal force is now. So I can use this equation, which I'm going to write down, because that's what you do. Write down the equation first before you start plugging numbers in. And that's 50, and this is 300. So mu is going to be 0.17. And we're expecting this to be a number between 0 and 1, so looks good. What would be the acceleration of the sled if mu was 0? Well, if mu was 0, then you'd get no friction. So that would be, if we wanted to just make a quick re-sketch of the force diagram, would have gravity still 300, normal force still 300, the pull still 50, but no friction. So now the unbalanced force would just be that pull, no friction to check the other direction. So mass times acceleration equals that force of pull. The mass of this thing is 30 kilograms, right? This is already multiplied by 10, so if you want to get back to the mass, you'd have to divide by 10. So I'd have 30 times A is equal to 50. So the acceleration would be 1.7 meters per second squared. All right, recognize that picture. Suppose a hanging 1 kilogram lab mass is attached to 4. So this is 4 kilograms here, and this is 1 kilogram here. Draw a force diagram for the block on the table. And we're talking about friction here, so there is some friction. So force of gravity is going to be 4 times 10. The support force is going to match that. Then I've got this tension force. I don't know how much, not yet anyway. And then I've got a friction force. Don't know how much of that either. So that's all I can do for right now. If the coefficient of friction is 0.2, then what's the acceleration of the block? Okay, so let's see. If the gotta write down that equation first. If the coefficient of friction is 0.2, I know the support force is 40, so that is 8, right? And I'm going to draw over here. You were not asked to do this, but I'm going to draw the force diagram for this too. So that has force of gravity. 1 kilogram times 10 is 10, and then force of tension. I'm making that look smaller because I know when this is released, it's going to accelerate like this, right? Just like that Einstein doll. And these tensions are equal to each other. So depending on how you did this, remember I gave you two options. You could write the two equations and add them together, or you can just do the what is the total unbalanced force mass total times the acceleration. So I will do this way. The total unbalanced force, as you look through this line of where it's moving, the tensions are going to cancel each other out. So I have 10 newtons in the winning direction here, minus the 8 newtons of friction. That's the total unbalanced force, right? These are balanced. These cancel each other out. So this winning, this losing, right? Gravity pulling down on this, friction resisting here. Total mass is 5, and the acceleration then is going to be 2 divided by 5, or 0.4 meters per second squared. Right? What would be the minimum value of the coefficient of friction in order for the block to remain motionless? Well, if the block's remaining motionless, then so is this. And if that is, the hanging one is remaining motionless, that means, I'm just going to do a quick redraw of the force diagrams. If the hanging block is motionless, that means the tension force must be balancing the gravitational force. And if the tension force there, like this, if the tension force there is 10 newtons, well, it's the same string, so that's also 10 newtons. Of course, gravity and the support force aren't going to change. Now, if everything's at rest, then this friction force must also be 10 newtons. Right? If everything's at rest, then all along this is going to be 10, 10, balanced, 10, 10, balanced. So now that means that the force of friction is equal to mu times the normal force. So now the force of friction is 10. Normal force didn't change, so the mu would have to be 0.25 to keep the blocks from moving. Number 3. A horizontal 100 Newton force is applied to a 50 kilogram classmate resting on a level tile floor, and a coefficient of friction is 0.15. Okay, so there's the person. Person's being pushed, I'm going to say in this direction, and by a 100 Newton force, and their mass is 50, so the gravitational force is 500. The support force, ain't nothing happening in that direction. That's going to be 500 newtons also. And the force of friction is equal to mu times the normal force. It's our new equation. So that's going to be 0.15 times the normal force and what is that, 45 or something? No, that's not right. 175 times 0.15. Yeah. All right. Good force diagram there. What's the acceleration? Well, unbalanced force here is the push is winning versus friction. So unbalanced force is mass times acceleration. Mass times acceleration is equal to, that's 100 minus 75, that's 25 divided by 50. So half a meter per second squared. Suppose the classmate was resting on a carpet where the coefficient of friction is 0.25. Is the horizontal force of 100 newtons, is it enough to get them to accelerate? Well, let's see. Quick resketch of the force diagram. I got my force of gravity is 500. My normal force is 500 newtons. The push is 100 newtons. And the force of friction is equal to 0.25, mu times normal force. So that's 0.25 times 500, which is 125 newtons. Now, that's impossible, right? You can't actually have 125 newtons of friction here, because that would be extra unbalanced force in the backwards direction, which would mean you'd push on them this way, and then friction would somehow like overcome you and make them go backwards. That doesn't work. It is possible that you push them and there's enough friction to resist, though. So this is like, instead of there actually being 125 newtons there, this is like the maximum possible friction that there could be. So what if you push with 100 newtons of force? Well, you're not beating this, so you're not going to get them to move. And that means friction is just going to match you to keep them from moving. That's probably the trickiest thing to understand about physics, about friction. Now, there's much trickier things than that in physics, I promise you. So if you want to, just a little visual here, if I were going to pull on this thing, let me give you a better visual here. So, I can push this thing across here. There is friction, and how much friction is there? Well, I could pull. So if I pull this thing at a constant velocity, it looks like there's about 0.8 or so newtons of friction. But notice if I don't pull that hard, like right now I'm pulling with half a newton of force, and it's not enough to make this thing move. So what would the force diagram look like for this thing? Well, it would be gravity, normal force, straight up, and then there'd be my pulling force, and there's just enough friction to counteract my pulling force. How come it's not like the point, come on. There we go. Oh, it's taking a little bit more now. Yeah, like 1.2. I told you, friction is just messy. It's so inconsistent. So yeah, it looks like 1.1, 1.2 is more like what we're getting there. So up until that point, friction just matches the pulling force to keep it from moving. We're not going to do a whole lot of problems that involve that. Usually we're just going to have situations where the object is moving and you use this equation, and whatever you get, that's how much friction there is. But I do want you to just have an opportunity to think about that a little bit. Okay, so what about on a slope? When you see a slope and you're thinking about, okay, my force of friction, here's my new fancy equation for friction. The thing about slopes is the normal force is not equal to the force of gravity, right? The normal force is going to be equal to the cosine component of the force of gravity. So you got to watch out for that. Since there's a slope, I'm going to go ahead. I know I'm going to make a force diagram. I suppose that's what this big space here is for. Get out your ruler if that helps you. There's the person, the skier. I'm going to turn back to this direction for just a minute so I can drop down my gravitational force. Force of gravity is going to be 84 times 10, 840. And then, now I'm going to turn this, because everything else is going to be in line now with my axes. And I'm going to turn on my calculator and make sure that I'm in degree mode. And I'm going to do the sine and cosine components of that. So I got 840 times the cosine of 20 degrees and 840 times the sine of 20 degrees. So I'm going to call that 790 and 290, just round to two significant digits. 790 and 290. Which one is which? Well, if you draw a good diagram, then you don't even need to think about SOHCAHTOA, because if we're talking about 790 and 290, obviously this is the shorter one, because look at the picture. And if your diagram's not great, then the skinnier angle is going to be down here. So that's opposite. That goes with sine, and then this goes with cosine. Okay, so how much support force is there? Well, the support force is perpendicular to the ramp here. That is going to be equal to this, not equal to that. So the support force, or normal force, is equal to 790 newtons. And how much friction is there? Well, the force of friction is equal to mu times the normal force. So mu is 0.15. The normal force is 790. So the force of friction, 790 times 0.15 is about 120. My calculator said 118.5, but I'm rounding to the nearest tens place here for my forces. So 120 newtons there. And that's it. If you're like, wait a minute, isn't there like a force down the hill, like force of motion or something? No, there isn't. It's this part of gravity that is making the skier accelerate down the hill. There is not another force in there. Okay, what's the value of the friction force? Oh, I just did that, didn't I? There it is. And then what's the acceleration of the skier? Well, the unbalanced force on the skier is equal to the force of gravity, but just the sine part of it. You put sine 20 there, I put a sine theta, whatever, minus the force of friction. Right? This is winning, this is losing. These are balancing. So unbalanced force is equal to mass times acceleration. The sine part of gravity is 290 newtons minus the force of friction. So the acceleration is going to be 170 divided by 84, which is about 2. And that, is that off the screen for you? Sorry about that. There it is. That's how you do some physics with friction. Takes practice. Got to go through and practice the problems on your own, right? It's fine to do it with a video, of course. That's why I put the videos up for you, but you got to try them on your own as well. And remember, there's a lot of value in redoing the same problems. Right? When you practice in free throws, you keep shooting basketballs at the same basket. There you go. See you later.